In this module, you will learn about different methods used to validate mathematical statements. We know that every mathematical statement is either true or false. We know that the truth value of a compound statement depends on the truth values of the component statements involved in it. How can we verify if the truth value of a component statement is correct? The answer to this question depends on the connective words, quantifiers, and implications involved in the compound statement. To validate such statements, we follow certain rules. Let's discuss the first rule. The first rule is used to validate compound statements with the connective word and or conjunctions. To validate whether a conjunction is true, we have to show that all of its component statements are true. P and Q are mathematical statements. To show that the statement P and Q is true, we need to show that both the statements are true. Let's check the validity of the statement. 2 is a positive number and a prime number. The component statements of the compound statement are: 2 is a positive number, 2 is a prime number. We know that component statements P and Q are true. Hence, it is validated that the given compound statement is true. Rule 2 is used to validate compound statements with the connective word OR. To validate whether a disjunction is true, we have to show that one of its component statements is true. If P and Q are mathematical statements, then in order to show that the statement P or Q is true, we need to show that either statement P is true or statement Q is true. Let's check the validity of the statement. 5 is a factor of 21 or 30. The component statements of the compound statement are: 5 is a factor of 21. 5 is a factor of 30. We know that statement P is false, while statement Q is true. Hence, it is validated that the given compound statement is true. Rule 3 is used to validate statements with if-then or implications. To prove the statement if P then Q, we need to show any one of the cases shown is true. By assuming that P is true, show that Q must be true. This is called the direct method. By assuming that Q is false, show that P must be false. This is called the contrapositive method. Let's prove the statement. If x is odd, then x squared is odd. The component statements of the compound statement are: x is odd, x squared is odd. To validate the given compound statement, let's consider that the statement P is true. Let x be 2n plus 1 for some integer n, by the definition of odd number. Therefore, x squared is equal to 2n plus 1 whole squared. On simplification, we get 2 multiplied by 2n squared plus 2n plus 1. This is also an odd number. This shows that x squared is also odd. Hence, the given statement is proved. Rule 4 is used to prove by implications. To prove the statement P if and only if Q, we need to show that if P is true, then Q is true. If Q is true, then P is true. Let's prove the statement. X minus 2 is negative if and only if x is less than 2. This statement can also be broken down as: if x minus 2 is negative, then x is less than 2. If x is less than 2, then x minus 2 is negative. Here both the implications are true. Therefore, the by implication is true. Hence, the given statement is proved. However, we come across some mathematical statements that cannot be proved directly. Such statements can be proved by the contradiction method. In the contradiction method, to prove a statement P is true, we first assume that P is not true, or negation P is true. Then, we arrive at some result that contradicts the assumption. This concludes that P is true. We cannot prove that a statement is false by the methods that we have discussed earlier. In such cases, the counterexample method is used to prove a statement. In this method, we take the example of a situation where the statement is not valid. Such examples are called counterexamples. 3 plus x multiplied by 3 minus x is not equal to 9 plus x squared for all integer x. This can be proved by taking a counterexample. Now, consider x equal to 0. Let's substitute the value of x in the given statement. On simplification, we see that 9 is not equal to 9, which is a contradiction. Hence, the given statement is false.